All right, good morning, everyone. So my name is Allison, and today I'll be presenting on SOT-MRAM. I know we already had a guest lecture on this topic, so I try to make the slides a little bit different and also tie together a lot of the concepts that we learned at the end of the last few lectures of class. So why MRAM? It really offers a lot of, it solves a lot of the issues with the limitations in SRAM, DRAM, and flash. So like flash, it is a non-volatile memory, but like SRAM, it is really fast. It also has about the same density as DRAM right now, so it's comparable to things that are already being produced in mass production. It also has very high endurance and also low write energy. A little bit, it solves the issue that SRAM has where it doesn't have the high leakage. And it doesn't need refresh like DRAM, and also it doesn't have the oxide degradation problem, or SOT-MRAM doesn't have the oxide degradation problem that flash has. So a little bit of a comparison between STT-MRAM, which we learned in class, and SOT-MRAM is that STT-MRAM is a two-terminal MTJ structure. This means that the read and the write currents go through the same path. This can cause degradation to your tunnel oxide barrier, which limits endurance really to like 10 to the 12 cycles, and also can have issues with redisturb, and the switching time is around 2 to 5 nanoseconds. SOT-MRAM, on the other hand, is a three-terminal device. So it has the MTJ and a heavy metal layer that is your write line. So because it's a three-terminal device, this means that it does take a larger area, so it has less density, but because you're decoupling your read and write with the three-terminal structure, your write current, which is your higher current, only goes through the heavy metal layer, which means you're not degrading your oxide barrier as much. So this allows for the endurance to get up to 10 to the 15 cycles, and because you have an independent read path, you're not likely to have read disturb issues, and the switching time is around 1 nanosecond, and like as we saw in the presentation from our guest lecture, it can be below 1 nanosecond now. So going over the device architecture, we have that heavy metal layer, so it's going to be a high spin orbit coupling material such as tungsten, platinum, tantalum, or a topological insulator. That's where a lot of the research is going into now. And this serves as your write channel. Then you have a tunnel barrier, typically MgO, that is sandwiched in between two ferroelectric materials, ferroelectric layers. The first is going to be your free layer. So this is the layer where your magnetization is going to switch, and this will determine the 0 and the 1 state. And then you have your pinned or fixed or reference layers. It goes by all of those names that when I was reading all the papers. And so this serves as your baseline for your TMR read process. Also important to note is that PMA, so perpendicular magnetic anisotropy, is preferred. This is for scaling purposes. With IMA, we need an elliptical MTJ structure, and so this is just going to be a little bit larger, but with PMA, you can get a circular MTJ, so it allows the device to be a little more dense. This also is beneficial if looking long-term at your photolithography process. It's much easier to print a circular structure than an elliptical structure consistently. So for your write operation, we're gonna use two key concepts. Your main one is gonna be the spin Hall effect, which we learned in class. So this occurs when an in-plane charge current flows through the bulk of the heavy metal layer and creates a transverse spin current via spin orbit coupling. So electrons with opposite spins are going to be deflected onto in opposite directions, and so you're going to have accumulation of spin at the interface of your heavy metal and ferromagnetic layers. And this ultimately is what is exerting torque on your free layer magnetization, causing it to switch. A key concept that we also learned in class is your spin Hall angle. So this quantifies the efficiency of your charge current to your spin current conversion. And then another key concept that is like a secondary effect is the Rashba-Edelstein effect. So structural inversion asymmetry at the interface creates an internal magnetic field. This just results in additional torque that aids in spin accumulation and switching. Also, going back to the LLG equation that we learned in class, I really want to emphasize the torque components of this to understand how magnetization affects our switching over time. So we have a field-like torque, which acts like an extra magnetic field. And then more importantly, we have a damping-like torque component to it. So this is going to be our primary driver for switching. This pushes the magnetization toward or away from the spin accumulated direction. And it directly opposes Gilbert damping. This allows for, or deterministic and fast switching requires for the damping-like torque to overcome the effective anisotropy field that keeps the magnetization pinned along the easy axis. Our read operation is a little simpler. So we pulse a small sense current through the MTJ. And then the key concept for this is our tunnel magnetoresistance, or TMR. So this allows us to sense whether it's in a parallel state or an anti-parallel state, and this is going to be your 0 or 1 state. So in our parallel state, the free layer and the pin layer, the magnetization is aligned in the same direction. So it's going to be this example. And this is going to be our low resistance state. Because the density of states are aligned for the density of states for the tunneling electrons match, the electrons can easily tunnel through the MgO barrier. And so this means it has lower resistance. In the anti-parallel state, or a high resistance state, the fixed layer and the free layer are in the magnetizations are in opposite directions. So the density of states have a mismatch, which means the probability of the electron tunneling decreases significantly, which correlates with a higher electrical resistance. The TMR ratio quantifies the difference in resistance. So a large ratio is needed to clearly distinguish between a 0 and a 1 state. And this is the equation that is our TMR ratio. So the resistance of the anti-parallel minus the parallel over the parallel resistance. So some main challenges to incorporating SOT into mass production is that, once again, we do need a really high TMR ratio, so our on-off ratio. Right now, it's around 150%, but the target is 250% for mass production. Also, we do need a really high write efficiency, so our spin Hall angle that I mentioned before, target is over 1. And then also, we need to make sure that all of the materials that we're using can be incorporated in the entire CMOS process, right? So our back end of line uses really high temperatures, around 400 degrees Celsius, so anything that we're adding or using has to be able to survive the really high temperatures used in back-end line processing. And also, as I mentioned before, we use a 3-terminal structure that does have, is less dense because of the larger area. So a lot of research is being done to move to a 2-terminal SOT structure that allows the SOT to be more towards the STT level density. Another key limiting factor to incorporating SOT-MRAM into commercialization is the need of an external magnetic field. So without the external in-plane field, we have a really non-deterministic switching due to the PMA. The SOT only pushes the magnetization to the plane, and then whether or not it switches to the positive or negative direction is just probability, so it's non-deterministic. But by adding an external field, we're able to break the mirror symmetry and drive it towards a deterministic switching. But obviously adding an external field will increase the area, make it less dense, and also increase the power consumption. So this is really also not ideal. A lot of research is being done right now to solve this issue. So some of the research is into in-plane effective magnetic fields with exchange coupling or chiral coupling, tilted PMAs with and then spatial non-uniformity with wedge capping layers, so like changing the structure to have drive your magnetization, spin current density gradients, and also a lot of research into different materials with low crystalline symmetry, low magnetic symmetry, and then also magnetic trilayers. So some key takeaways from my presentation are SOT-MRAM really targets the memory gap. So it combines SRAM speed with DRAM density and flash non-volatility. Decoupling the read and write paths really helps with our endurance. And so because we don't have that current going through the tunnel barrier, and also field-free switching is one of the critical problems that we need to reach commercialization. Thank you.